you all in the continuation of last class. So I proved the Helmholtz vorticity equation in MHD, not vorticity equation, Helmholtz equation in MHD. As you know, in fluid mechanics also you have derived Helmholtz equation and Bernoulli's equation. Okay, so here also we are going to derive the Bernoulli's equation in MHD. In MHD means the special case is, so in fluid mechanics you come across, there will be the magnetic field is zero. But in fluid mechanics there will be the presence of magnetic field. That's why in Bernoulli's equation you can find the magnetic term. That's enough. So nothing will be changed except the magnetic field term. Okay, let us see how it appears and how it come in the Bernoulli's equation and how to derive the Bernoulli's equation in MHD. Now please come to my notepad. The Bernoulli's equation, N-O-U-L-L-I, apostrophe S, Bernoulli's equation in MHD. Okay, in MHD. Now, to get Bernoulli's equation in MHD, you have to integrate the momentum equation for, this one, ideal fluid. Ideal fluid means no viscosity. Okay, so as you used in this one previous derivation, you have to take the ideal fluid means your viscous term mu into del square q is equal to 0. In your momentum equation, this term is equal to 0. Therefore, to get Bernoulli's equation in MHD, you have to derive the momentum equation for ideal fluid along the streamline between the points 1 and 2. Between the points 1 and 2. Okay, so you know the Bernoulli's equation, the momentum equation for the ideal fluid is rho into del q by del t plus q dot del of q is equal to minus gradient of p plus rho into g plus mu into, this is magnetic permeability term, not viscosity. Okay, so here there will be change in permeability. So for viscosity you are going to take some mu h, or this one has different. Okay, but now you have only magnetic term. That's why I am going to take it as mu into j cross h. Mu into j cross h. Okay, but in the previous class I told you from Ampere's law you can express j as curl of magnetic field. Okay, that's why this term will become, so what it becomes, this is nothing but minus gradient of p plus rho into g plus mu into del cross h cross h. Is it right? Del cross h cross h. From vector identity you know gradient of A dot A is equal to A dot B is equal to A dot del of B plus B dot del of A plus A cross del cross B plus B cross del cross A. This is the vector identity. By replacing both A and B by H, you will get gradient of H dot H. I think we have already derived in, so your Helmholtz, Alfvén theorem, I think so, Alfvén theorem. So this will become H dot del of H. This is again H dot del of H. That's why it becomes 2 times H dot del of H. Plus this is H cross del cross H. Is it? Again it also becomes H cross del cross H. That's why it will become 2 times. By simplifying you will get, so del cross H is equal to, look here, by interchanging these two, the sign will become negative sign and this will come to the left hand side, that becomes plus, and by cross multiplying 2, it will become h dot del of h minus gradient of 1 by 2 h square, because h dot h is h square, and by multiplying this 2 you are going to get 1 by 2 h square. Now by substituting this here, you are going to get rho into del q by del t plus q dot del of q. So cross multiply this row, then minus 1 by rho into gradient of p plus g plus h dot del of h minus gradient of 1 by 2 h square. Is it? You know, the gravitational force is conservative in nature, that's why you can write it as gradient of some, so scalar, omega or phi or whatever the thing, no problem. This scalar is nothing but gravitational potential. Okay, gravitational potential, right? So you can express G as minus gradient of omega. So this omega is nothing but gravitational potential, right? So now by substituting this, you are going to get minus 1 by rho gradient of P minus gradient of omega minus. So here you have to multiply with this by mu, because in the equation you have mu term, right? That's why you have to take mu. So then it will become mu into gradient of mu into h square divided by 2. Okay, this equation, this term, plus this is mu into h dot del of h. Okay, so this is the equation you are going to get. Again, this term can also be expressed using the same relation as, so what you are going to get, instead of h, if you are going to take q, this equation will becomes gradient of q square is equal to 2 times q dot del of q plus 2 times q cross del cross q. Is it right? Okay. Now, so you want this term, that's why again by taking 2 common and by cross multiplying this, so and rearranging the terms, you are going to get q dot del of q is equal to, okay, so gradient of 1 by 2 q square minus q cross omega. I am going to write q cross omega, because you know the vorticity vector omega is written as del cross q. Okay. Now substitute this term in the equation of, momentum equation, right? So by substituting this here, you are going to get del q by del t, okay, minus q cross omega is equal to, I am going to take this term to right hand side, that's why it will become minus 1 by rho into gradient of p minus gradient of omega minus gradient of mu h square divided by 2 minus gradient of 1 by 2 q square, okay, plus the remaining term mu into h dot del of h. Is it? Okay. Now, so we can integrate this equation, so between the limits 1 and 2, but we are going to integrate this equation for 2 cases. One case is, case 1 is nothing but, suppose the flow is steady, okay, steady flow. Suppose the flow is steady, it means del q by del t is equal to 0. Then we have to integrate. Similarly, Suppose the flow is not steady, means unsteady. Unsteady means this term is not equals to 0, but the flow is irrotational. Once the flow is irrotational means your vorticity vector becomes 0, means del cross q is equal to 0. Is it right? Del cross q is equal to 0. For these two cases we have to integrate. First case is steady flow. Second case is unsteady but the flow is irrotational. Now I am going to take the steady case. For steady case, case 1. Case 1 means steady case. Steady case means del q by del t is equal to 0. For this it will become minus q cross omega, because del q by del t is equal to 0, minus gradient of, look here gradient is common in all these four terms. That's why you can take gradient operator outside and you can apply the operator wholly, right? So it will become, minus gradient of integral dp by rho. This is possible only when you are going to take barotropic condition. Otherwise it is not possible to write in this form. Okay. And plus omega plus. So this is frozen inflow condition. If you are going to assume the frozen inflow condition, then you can write it as by 2 whole divided by rho, because you have to take rho inside. The frozen inflow condition, H is proportional to density. Barotropic condition, pressure is proportional to density. By taking these two, you can express, okay, so gradient of P by P as like this, okay. Similarly, gradient of mu h square by 2. So here outside 1 by rho can be written as like this. This is for frozen inflow condition, this is for barotropic condition, plus 1 by 2 q square, plus 1 by 2 q square. So and plus mu by rho into, h dot del of h. I think here I forgotten rho, because here also once you divide rho throughout the equation, it will appear here also. That's why here also you are going to get 1 by rho. Here also you are going to get 1 by rho. Okay. So now this equation will becomes, we have to integrate this equation between, points 1 and 2. Between the points 1 and 2, then this equation can be written as minus integration from 1 to 2 of q cross omega dot ds is equal to minus integration from 1 to 2 of gradient of, look here also integration, here also integration. You can write integration of, okay, dp by rho plus d of mu h square divided by 2 by rho. Okay. This is not. So for these two, and plus 1 by 2 q square plus omega. Now close the bracket. The gradient will apply for all these terms, plus integration from 1 to 2. So mu by rho into h dot del of h into, dot ds. Right. Here also dot ds. Got it? Now, look here. From these three terms, you can take these three terms, that is q cross omega dot ds. It is nothing but vector triple product. You can express it also. Omega dot ds cross q. You can write this as, we have observed the concept in the Alphen wave theorem also, and there I have given additional video regarding the clarification of this term. Okay. So you can write, this is the vector triple product. You can express in this form also. Here the surface and velocity are in the same direction, means they are parallel. That's why that term must be equal to 0. They are parallel. That's why that term must be equal to 0. Now, the above equation can be written as, okay, ಏನು ಬರಿಬಹುದು? 0 is equal to minus integration from 1 to 2 gradient of so and so plus 1 by 2 q square plus omega. This is applied for the gradient dot ds plus 1 by 2 into same terms. Whatever the terms are there, same terms. Okay. Now, look here. So, gradient of these terms means, inside the gradient you can find these. Integration dp by rho, integration d mu h square by 2 into rho plus 1 by 2 q square plus omega. I am going to call this total term as some f. Okay, I am going to call this total term as some f. Right? Okay, some f. Then your integration will become 0 is equal to minus integration from 1 to 2 gradient of f dot ds plus integration from 1 to 2 mu by rho into, okay, so h dot del of h dot ds. Now, look here. Del f means, for this term I am going to express. This term means it is nothing but, del f by del x plus del I into I plus del f by del y into j plus del f by del z into k. Dot ds means dx into I plus dy into j plus dz into k. Okay. By taking the dot product you are going to get del f by del x into dx plus del f by del y into dy plus del f by del z into dz. Is it right? By taking the dot product of these two, you are going to get this equation. But this is nothing but what? It is nothing but the total derivative of f. Is it right? You know this concept. We have used several times in the previous classes. Okay. So, this is nothing but the total derivative. That's why your term df dot ds can be written as df. Therefore, 0 is equal to integration from 1 to 2 of df plus integration from 1 to 2, this is minus sign, plus, so or you can write, so instead of writing like this, you can write this as integration from 1 to 2 df is equal to integration from 1 to 2 mu by rho into h dot del of h dot ds. Now, this integration is not possible unless this term is equal to 0. But you know that in MHD, Lorentz force is not 0. Okay. So, Lorentz force is not 0. Generally, this is not a 0 because Lorentz force is not a conservative force. Suppose h dot del of h is equal to 0, means I am going to take if h dot del of h is equal to 0, then your equation will becomes, so f is equal to a constant. Upon integration, you are going to get, so if suppose h dot del of h is equal to 0, then upon integration, you are going to get, so f is equal to a constant. F means what? F means, integration of dp by rho plus integration of derivative of mu h square divided by 2 whole by rho plus 1 by 2 q square plus omega. This is nothing but your f. Okay. Is equal to constant. I am going to call that constant as some beta. And this is the required Bernoulli's equation for study case. And this beta is a constant. And it changes, this beta changes, even it is constant, but it changes from one streamline to another streamline. Means it is constant for one particular streamline. If you are going to change the streamline, then beta will differ. Okay. Suppose the fluid is homogeneous. Okay. homogeneous fluid. You know what is homogeneous fluid? Homogeneous means the density is constant everywhere, and each and every layer the density is constant. So that's why, so once if it is homogeneous, then your Bernoulli's equation will become simply P by rho plus mu by rho into h square by 2 plus 1 by 2 q square plus omega is equal to constant beta. This is nothing but the Bernoulli's equation when the fluid is homogeneous. Okay, when the fluid is homogeneous. Now we shall go for the case 2. What is the case 2? Case 2 is the flow is unsteady, but it is irrotational. Flow is unsteady means del q by del t is not equals to 0. But irrotational means the vorticity vector omega is equal to 0. Flow is unsteady, but vorticity vector is 0. Vorticity vector is 0 means del cross q is equal to 0. Once del cross q is equal to 0, you know you can express velocity as some gradient of some velocity potential phi. So we have used this concept several times previously. So if del cross curl of q is equal to 0, then q can be expressed as minus gradient of phi. Minus gradient of phi anta baribodu. Artha aita? Right? So that's why, so now, so come to the original equation, that is, so del q by del t plus q cross omega, minus q cross omega is equal to minus gradient of, same thing, integral dp by rho plus mu, omega plus integral derivative of mu h square divided by 2 whole divided by rho plus 1 by 2 q square. Okay, so plus mu by into ds dot ds. I am not integrating here. Mu by rho into h dot del of h dot del of h. So this is the equation. But here we assume that so omega is 0, that's why this term tends to 0. Remaining is this term and these terms, right? But you know, once the flow is irrotational, you can express q as minus gradient of phi. That's why this term will become del by del t of, look here, del q by del t can be written as del by del t of minus gradient of phi. Is it right? Minus gradient of phi. Okay. But minus gradient of phi, this is differential operator, this is the differential operator. You can write it as minus gradient of, so you can write it as, so del phi by del t. Instead of writing like this, you can also write this in this form also. That's why, so this term will becomes minus, so gradient of, minus gradient of del phi by del t, where phi is velocity potential, is equal to right hand side as it is. Now you can see, you can take this term to left hand side also, or take this term to right hand side also, whatever the thing. So as you wish. So now by doing like that, you can get, right? So by taking this term to this term, they will become plus and this is minus. That's why gradient of integral dp by rho plus derivative of mu h square divided by 2 whole divided by rho. This is the integral, okay? Plus 1 by 2 q square plus omega minus d phi by dt. Okay, d phi by dt, right? Del phi by del t. So del phi by del t, and the remaining term plus mu by rho into h dot del of h, mu by rho into h dot del of h. Upon integration again between the points 1 and 2, between the points 1 and 2, integrating from 1 and 2, integrating from 1 and this is equal to not plus, because I have taken those terms to this side. This is equal to, this is upon integration equation from 1 to 2 of this dot ds and this dot ds. This equation will becomes like this. Okay. Look here. Here again this term can be written as derivative of, total derivative of some f, because I explained how to write this term. Okay, that's why this will become integration from 1 to 2, derivative of f, total derivative of f is equal to integration from 1 to 2 of mu by rho into h dot del of h dot ds. Okay, dot ds. Now, look here, again unless this term is equal to 0, it is not possible to integrate. So, but if this term is equal to 0, then we can integrate. So, after integration you are going to get f is equal to a constant as same in the previous case. But, so that f is nothing but the terms integral dp by rho plus integral derivative of mu h square divided by 2 whole divided by rho plus 1 by 2 q square plus omega minus del phi by del t. So is equal to a constant. I am going to call that constant as some beta, and this beta is varies from one streamline to another streamline. If we assume this is true for a barotropic and frozen inflow condition, suppose if you are going to assume, if you are going to take the fluid is homogeneous, then this term will become simply P by rho, and this term will simply becomes mu h square divided by 2 rho, and the remaining term as it is plus 1 by 2 q square plus omega minus del phi by del t is equal to beta. This is the required Bernoulli's equation for the unsteady case, and the flow is irrotational. So flow is unsteady and irrotational, then the Bernoulli's equation is given by like this. Okay, it is also very important to the point of examination. So observe carefully and go through the notes. Surely you will convinced with this video. So do well. So if you have any doubts, please don't hesitate to put a message again, right? So all the best. Thank you.